Welcome to Know-How. In this video, we will look at capacitors in series and what the equivalent capacitance would be. So let's take two capacitors, C1 and C2, that are connected in series. This is C1 and C2. Now let's short them across a voltage source V and complete the circuit here. So now once the switch is closed, there would be a charge, positive charge, stored on the plate of the capacitor C1, which will induce a negative charge on the other plate, the bottom plate of the capacitor C1. Now the top plate of the capacitor C2 will be deprived of the negative charge and develops a positive charge, which will in turn develop a negative charge on the other plate of the capacitor C2. So that's how it works. And now if you look at the voltage dropped across the capacitors C1 and C2, the voltage across capacitor C1 is V1, the voltage across capacitor C2 is V2. So now we can write the total voltage across the circuit V is equal to V1 plus V2. Now we know that the charge across the first capacitor C1 is Q1, which is C1 V1, and the charge across the second capacitor Q2 is C2 times V2. And when we looked at the charge accumulation, we see that the charge developed across both the capacitors is the same. So Q1 is equal to Q2. So now, which means C1 V1 is equal to C2 V2. So we can also write V1 is C2 V2 over C1. And we also know that V1 plus V2 is the total voltage developed, which is V. So V is V1 plus V2, and V1 can be written as C2 V2 over C1 plus V2, which is V2 times 1 plus C2 over C1. So the total voltage is that, and then we can write V2 as V times C1 over C1 plus C2. Similarly, we get V1, the voltage across the capacitors C1 would be total voltage multiplied by C2 over C1 plus C2. Now, if we look at the charge across the capacitor C1 is Q1 is C1 V1, which is nothing but V times C2 over C1 plus C2 multiplied by C1. That is the total, and the Q1 can also be written as C equivalent times V, which is C1 C2 over C1 plus C2 times V. So C equivalent of the parallel combination is C1 C2 over C1 plus C2 of the series combination, So now if you look at it, when you connect two capacitors in series, the equivalent capacitor is smaller than is C1 and also smaller than C2. Now this whole thing can be proved in a different way. That way is, we can look at the voltages across the capacitors. So V across a capacitor, Vc of t, is 1 over C integral I of t dt. So now what we can do is, since the capacitors are in series, so you got the two capacitors C1, C2, the same current I flows in both of them, through both of them. So this is the voltage V. So this is the total current I going in there. And now, so V1 of t is equal to 1 over C1 I integral I of t dt. V2 of t is 1 over C2 integral it dt. And we know that V1 of t, the total applied voltage V of t, is V1 of t plus V2 of t. And the total applied voltage can be written as 1 over C equivalent integral I of t dt, which is V1 and V2. We have the equations here. So when you put that substitute in, you get 1 over C1 plus 1 over C2 integral I of t dt. So from this we obtain 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So if you add more capacitors in series, you can keep adding 1 over C3 plus and so on. So now if you take again the series combination of the two capacitors, if you compute C equivalent, you would get C1 C2 over C1 plus C2. So the same as what we obtained when we looked at the charge stored across the capacitors. We got the same value in there using this method, as well as looking at the current or voltages dropped across the capacitors.